Dear students, welcome to my YouTube channel PCM Academy. If you are new in this channel, then please subscribe my channel, because if you are a student of physics, any level of physics from class 11 to up to MSc level, any level of physics is discussed in this channel. So this will be very helpful for you. But now we are continuing our lecture series for revision course on mechanics, basically that is basically for MSc entrance exam. And in the last class I have discussed about some velocity and acceleration in plane polar coordinate, in cylindrical coordinate as well as in spherical polar coordinate. Now in this class we will discuss about the properties of central forces. Okay, so let me tell you about one by one the important properties of central forces. Then we will discuss some problems also. Okay, so first of all about central force, you can tell that it is only the function of r. So it is only depend on the radius, because this is the function of only r. It does not depend on the angular variables. It is only the variable of radial distance. Okay, so it is always from a point, it is always outwards or inwards. So we can write it as plus minus. Suppose if you want to denote it in vector form, then you can write it in plus minus form. Okay, because it is always from a particular point, either it is outwards or inwards. So for inwards there is attractive force, and for outwards there is a repulsive force. Okay, but it is always denoted as f of r, because this is only the function of r. And the very second one is that the torque acting on the particle which is moving under central force will always be 0, because you know the definition of torque is r cross f, and here r is r cap and f is obviously f of r cap. So r cap dot r cap cross r cap is always 0. So torque will be 0, that means dj upon dt is equal to 0, because rate of change of angular momentum, here j is nothing but the angular momentum. As you know, the rate of change of angular momentum is actually the torque. So dj upon dt is equal to 0 as tau is equal to 0. So j will always be constant. So under central force motion, the total angular momentum of the particle is always be 0, because the external torque acting on the particle is always 0. And if you talk about the r dot j, that is the radius vector and the angular momentum, if you take the dot product of these two, and you know j is nothing but r cross p, where p is the linear momentum. So here you can see from the properties of triple product that r dot r cross p is equal to 0, because in triple product if any two vectors are equal, then its product will be 0 always. So it will be r dot r cross p is equal to 0. And what it means? It means that r is always perpendicular to a constant vector, because you know r cross p is j. So r dot j is 0 means r is always perpendicular to a constant vector, and that is only possible if the motion is confined in a plane. So the very third property of central force, you can say the motion is confined in a plane. And then we have already discussed in plane polar coordinate, because as it is the motion in a plane, so if you talk about the plane polar coordinate, if we describe the motion of a particle under central force in a plane polar coordinate system, then its radial component of force will be this, and the transverse component will be this. But as we have said earlier that f is only the function of r, so your fr will be am r double dot minus r theta dot square, but your f theta, that is nothing but am r theta double dot plus 2 r dot theta dot is equal to 0. Here r dot means dr upon dt, and theta dot means d theta upon dt, that is the angular velocity. So this component will be 0. And if you rearrange this term in this way, the d dt of m r square theta dot, because you know the derivative of this is nothing but this r theta double dot plus 2 r dot theta dot, so that will be 0. What it means, this am r square theta dot is nothing but the angular momentum. So the rate of change of angular momentum is 0, that means j is equal to constant again, and here we have taken only the magnitude of j. Okay, so we can write this also from here. And the areal velocity, that is dA upon dt, we can prove this also under central force motion, that dA upon dt j upon 2m, where j is the angular momentum and m is the mass of the particle. And as you know that j is constant and m is also constant, so dA upon dt is constant, so the areal velocity under central force motion is constant. These are the properties that I have write down here, but all the properties I don't give you the proof. Where the proof is required, I will tell you, because our goal is actually to solve problems by using the properties of central forces. Because this is a revision class, if you want to take the detailed class, I will upload later on. But now this is a revision class, so you have to know each and every point, every key point which will help you to solve problems. Okay. And the total energy of a central force is the kinetic energy term, you know, half m v square, and v here is r dot square plus r square theta dot square. If you can't understand these kinds of terms, this r dot square, r square theta dot square, or these terms, then you can see the last video that I have uploaded on velocity and acceleration in different coordinate system. You will easily find that this is the velocity square of a particle moving in plane polar coordinate system. So this is the kinetic energy term, and this is the potential energy term, and these two will be the sum total of these two will be constant. The total energy under central force motion will always be constant. And the last one is that central force is conservative in nature. So obviously you know the properties of conservative force, the curl of f is obviously 0, and if curl of f is equal to 0, then f can be written as the gradient of a scalar function that is called potential. So we can simply write it in this form also instead of gradient, that is f of r is equal to minus del v upon del r into r cap. Otherwise in general you can write that f is nothing but minus gradient of v. So you can write in this way also. But here we will use this as f of r is only the function of r. So you can write in this way also that f of r is equal to minus del. We have the magnitude of f of r is minus del v upon del r. So we can write the form of f of r, that is mass into acceleration in radial component, and the acceleration along radial component is r double dot minus r theta dot square, and that is equal to minus del v upon del r. So you just write this equation in this form. Now if you put the value of j that we have discussed earlier, that j is nothing but m r square theta dot, then we have this equation, because you know this m r dot will be same, r double dot will be same, and if you put here instead of theta dot we have j by m r square, and if we put theta dot square then we will get j square upon m r cube. So this is also equal to minus del v upon del r. So we can write in this two form this equation f of r is equal to minus del v upon del r, introducing the radial component of the acceleration and the angular momentum, magnitude of angular momentum m r square theta dot. Now let me derive this form with this two expression for circular motion, for uniform circular motion. So for uniform circular motion, if you talk about at r is equal to r0, that is the radius of this circular motion, then obviously as the radius of the circle is constant, so the derivative of this r dot will be r, that is r dot will be 0, and as it is a uniform circular motion, so theta dot is nothing but omega 0, that is also constant the angular velocity. Now this angular velocity can be find out by putting this value in equation 1. Now from equation 1 you can see, if we put that r is equal to r0 and r dot is equal to 0, so r double dot will obviously be 0. So if you put here r as r0 and this m will be multiplied with this, so m r naught, and this is omega 0 square or omega naught square, that is here theta dot. Okay, and here in this side it will be del v upon del r at r is equal to r0, because this minus sign and minus sign will be cancelled out, and from here we can see that omega 0 is equal to root over 1 upon m r naught del v upon del r at r is equal to r naught. Now if you put this value in equation 2, then what you will get, again this term will be 0, and this term will be at r is equal to r0 will be equal to this term at r is equal to r0. Now again this minus sign will be cancelled out. So these two equations for circular motion you should remember, we will use directly these two equations in problems. Okay, so for uniform circular motion, if you want to know about j, then we will directly use this equation, and if you want to know about omega 0, then we will use this equation. So let me solve one problem based on these two equations, that you can understand how we can use these two equations. Okay, image a particle of mass m interact with potential v of r is equal to half k r square and execute circular orbit with radius r naught. Find angular velocity and angular momentum. So angular velocity means omega 0 and angular momentum, that means j. So we have to find out omega 0 and j. So we will use the result directly that we have already derived. So for angular velocity, what will be our result? So our result is nothing but omega naught is equal to root over 1 upon m r naught into del v upon del r at r is equal to r naught. So we have to find out del v upon del r. So what we have v of r is equal to half k r square. So obviously what will be del v upon del r? So del v upon del r will be half k into 2r. So 2 will be cancelled out, so it will be just kr. Now if you talk about del v upon del r at r is equal to r naught, then here will be kr naught. So kr naught will be del v upon del r. So if you put here directly, so you will get what? Root over 1 upon m r naught into del v upon del r, that is nothing but kr naught. So r naught will be cancelled out, so it will be root over k by m. It will be root over k by m. Okay, so our angular velocity will be root over k by m. Now if you find out, if you want to find out j, that is the angular momentum, so what will be our equation? And our equation was that is j square upon m r naught cube at r is equal to r naught is equal to nothing but del v upon del r at r is equal to r naught. Now we have already find out del v upon del r at r is equal to r naught is k r naught, so we can write over here it is k r naught. So it will be nothing but j square upon m r naught cube is equal to k r naught. Now if you multiply this term with this, so we will have j square is equal to km into r naught to the power 4. So what will be j? So j will be r naught square root km. So this will be our j, and our omega is nothing but root over k by m. So now if you know the potential, then you can easily find out j for this motion and obviously omega 0 for this motion, and if the motion is in circular path. Now we will discuss later on for elliptical path also by using the effective potential, that I will come to.